Hello and welcome everybody to today's lecture about protection in electrical power systems. Today I would like to look with you into the peripherals, and here especially the current transformers and their linearity is in our focus. So if you have a network and there's a line, suddenly a fault occurs, we want to know how big is this current. For this purpose we insert a current transformer, and on the secondary side we have the relay which observes this current and takes its conclusions. So there is the primary current which is transformed into a secondary current, which goes to the relay. Now what happens in this current transformer? A current transformer is a transformer, and therefore we can represent it by the T-equivalent circuit diagram. The T-equivalent circuit diagram is made up of the ideal transformer, which has the ratio n/1, and, which is very important in this case, the transversal magnetizing impedance. And on the output of this transformer we have the secondary circuit. And now we see the current comes in, the primary current, it is reduced by the factor of n in the ideal current transformers, and now it is going into either the secondary circuit, which I have dissolved into the lead resistance, the contact resistance and the relay resistance itself, and also into this transversal magnetizing inductance. So the current now, which comes in, has two options where to go. It can go into the relay, which is a path which we want, and it can also go down into the magnetizing impedance, which is something like a shunt impedance, and that reduces, of course, the output current. And also, while it does so, there is a voltage across the terminals of this current transformer, which is made up of the current times the burden resistances. So this magnetizing reactance has a peculiarity. Since it is normally carried out as an iron inductance, we have a strong magnetizing curve, which you see at the bottom. We see that as the voltage across this inductance raises, suddenly the current is increased, and this means we have a loss of leakage current, which is detrimental to the purpose of this current transformer. So we see the relay current is the difference of the incoming reduced primary current and this magnetizing current, and the voltage is just the product of the relay current times all these impedances. And this should always be below the so-called knee point voltage, or some people call it saturation voltage of the current transformer. This is the voltage where the current in this transformer is no more linear to the voltage. Now let's look into this. I give you an example where the EMF, that is the voltage across this transversal magnetizing reactance, is below this magic knee point voltage. Here we see that we have a small magnetizing current, and if we put this into a Sankey diagram of the current, we see the input current is reduced, then we have a small part that is diverted and all the rest goes into the relay, and this is what we want. In contrast to that, we look into the same situation, but now with an elevated EMF, an elevated voltage across the internal transversal magnetizing reactance. In this case, we have a big magnetizing current, and the useful current, which the relay should see, is reduced. And this is no more a replica of the primary current, and we do not like this. So the question is, how can we determine, is it going right or wrong? So what is the EMF? Is it below this knee point voltage or above? Now we take step one. We standardize the burden situation. Standardized means we take for all values the nominal values, the nominal current for the current transformer, the nominal current for the relay, the nominal relay burden or secondary burden of the current transformer, and by doing this, we see that this nominal EMF, the nominal voltage which the transformer has to sustain under nominal load voltages, is this given here, the nominal EMF, is the product of the current and the burden plus the internal resistance of the current transformer. In step 3, we go now to the marginal situation. The marginal situation is characterized by the overcurrent factor or the limit of this current transformer, which is normally given by a factor like a figure of n, for example. So we increase the primary current by this factor of n, and of course everything is multiplied by this factor of n, and the EMF, that is the voltage across the transversal magnetizing reactance, is also increased by the factor of n. And we just must check that this is below the knee point voltage. And if it's so, then we're in a good position and the transformer performs its duty as it should. So this was today's lecture about current transformers, their linearity, and I thank you very much. I'm looking forward for the next lecture with you. Thank you very much.